Today we're learning all about inverses of functions. So we're going to start off with this example of our quadratic function g of x equals x squared plus 2. So first we're going to list 7 ordered pairs that belong to g of x, and we're going to use the x values of -3, -2, -1, 0, 1, 2, 3. So that means that when I plug in or substitute -3 into my function, then I should get 11 as the y coordinate. -2 squared plus 2 will give me 6. -1 squared plus 2 will give me 3. At x equals 0, I'm going to have a y value of 2, and that's my vertex, so then the other points are just going to have the mirrored y coordinates. Next, it's very important for us to notice that the definition has been given to us. The inverse of g of x is found by switching the coordinates in each ordered pair. So that means that all we need to do to get the inverse is simply 11 -3, 6 2, 3 -1, 2 0, 3 1, 6 2, and 11 3. So now let's start graphing the function and its inverse. There. 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 1, 2, and one more. That one's a little bit off, so let me try to just do a little bit better. Okay. We're going to draw our parabola now. Okay. And now we're going to take our inverse points, and we're going to graph those now. And there we go. So we have our original g of x function up here. Okay. And this one we're just going to label as inverse for now. Next, when we try to answer the question of is the inverse a function or not, we would take a look at, let's say right here or right here. We could draw a vertical line along any part of this inverse graph function, and it would cross through 2 points simultaneously. So that means that this inverse graph fails the vertical line test. So this is actually just a relation, not a function. In terms of the relationship between the two graphs, I'm going to highlight some points here. You can see that, let's say, for example, this point right here becomes this point here on the inverse when we switch the x and y coordinates. And then this point is now going to become this point. This point is now this point, and so on and so forth. So this mirror line that I'm asking you to find is actually the line y equals x. So let's do some practice. For the relation that is the inverse of this function, we simply have to switch the, so we have 1, 4, 2, 9, 3, then 16, 4. And in terms of determining if this is a function or just a relation, we can conclude that yes, this is a function since every x has one unique y value. And for the next example, just to drive the point home, we have Ann, Bob, Sue, Bob, Kate, Al as a function because every sister sibling, and Sue, Kate, has one brother, either Bob or Al. But now if we take the inverse of such a function, then that means that we are now going to get Bob, Ann, Bob, Sue, and when we look at this new relation, we can see that it's not a function because Bob, the x variable value, has two sisters, Ann and Sue, which would be considered the y variable values. So let's summarize some key ideas that we've now discovered about inverses. First one is that the inverse of a function is the relation that is created by switching x and y. So that's the very key concept about inverses. Everything else, such as the next point, the inverse of a function is not necessarily a function itself. That comes from the fact that we switched x and y. Okay. And then because we switched x and y, we also see that the inverse relations graph is the reflection of the original function in the line y equals x. And then the last point here, the domain and range of the function are now going to become the range and the domain of the inverse. Okay, just like because we switch x and y in order to create the inverse, that means the domain of the function becomes the range of the inverse, and the range of the original function will become now the domain of the inverse. So for finding the algebraic model for the inverse relation, we have to understand what inverse really means. Okay, now inverse, when we talk about algebraically, inverse actually means to do the opposite operation in backwards order. Okay? So if you have this function f of x equals 5x plus 8, that means we start off with x, we're going to multiply it by that 5, and then we're going to add 8. So the order of operations is first we're going to multiply by 5, and then lastly we're going to add the 8. Okay? If we want to get the inverse, which means to do opposite operations in backwards order, then that means we're going to take that x, and instead of multiplying by 5 and then adding 8, we have to do opposite operations in backwards order. So then the first thing we're going to do is to take that x and subtract 8. And then after we subtract 8, instead of the multiplying by 5 operation that we had here, we're going to do the opposite. So we're going to divide by 5. So that means that the inverse relation will be y equals x subtract 8, divide everything by 5. And really, this is the same thing as taking 1/5 of x minus 8. Because if you take something and divide it by 5, that's the same thing as multiplying by 1 over 5. Okay? So this process of doing the opposite operations in backwards order, it can take a long time, especially if you have more complex functions that you're supposed to be working with. So in order to do this algebraically, what you can do is follow these steps that we've outlined here. First, if you see an f of x, you're going to replace it with y. So this f of x up here, we're going to rewrite that as y equals. So we're going to say y equals 5x plus 8. Okay. Then we're going to interchange or switch x and y. So that means we're now going to write this as x equals 5y plus 8. Then, because we've now switched x and y, we're going to work on isolating for this new y. Okay, so that means we are going to subtract to get 5y, and then the last thing we're going to do is we're going to divide both sides by 5. So we get x over 5 equals y. And now when we take a look at this, because our x here is in our numerator, we can see that this is actually a linear function. Some people get this confused and think that it's a rational, but this would not be a rational function right here. Yes, this would actually be linear because it's x to the exponent of 1. So we're going to rewrite the y as f inverse x equals x minus 8 over 5. And one correction that I'll make to the notes for number 4, replace y with f inverse x if the inverse is a function, otherwise express as, you can just cross out g of x and just leave it as y. Okay, so we're going to try our best to express functions using function notation, and if it's a relation, then we're just going to write y equals. Okay, so let's go over these examples here. You have f of x equals 4x minus 8, and we want the inverse. So first, we're going to write this as y equals 4x minus 8, and then we're going to switch x and y, so we get x equals 4y minus 8, and then we're going to do opposite operations in backwards order. So we're going to have x plus 8 equals 4y, and then we're going to have y equals x plus 8 over 4. Again, taking a look at the placement of our x, it's in the numerator, so that means that this is a degree 1 polynomial, so that means that this is actually a linear function. Okay, it's a line with a slope of 1 over 4 and a y-intercept of 2, so that means that we can express this as a function. So therefore, f inverse x is equal to 1 over 4x plus. For the next example, again, we're going to rewrite y equals x squared, and then we have x is equal to y squared because we switched x and y, and now we want to get y by itself. So anytime we go from square to taking the square root, you have to take the positive and negative square root, like so. Okay, so we have y equals plus minus root x. And if you remember back from one of the first lessons of this unit, anytime you see this plus minus in front of root x, this indicated to us that this was just a relation, okay, not a function. So we're not going to replace y with f inverse notation. Let's finish off our last couple of examples. So we have x is equal to y squared plus 3. So now we're going to isolate for the y squared, and then we're going to end up taking the plus minus square root of x minus 3. And again, as soon as you see that we have this plus minus, that means that we have just a relation, not a function. So we're not going to replace y with f inverse. We're just going to leave this as is. in our last example here, this is the rational function. So we're going to write this as x equals 1 over y. Now, in order to isolate for this new y that we have, what we're going to do is we're going to multiply both sides of this new relation with, sorry, not x, by y. Okay, so that means that on my left side I have x, y, and on the right side I have 1. Okay, because this 1 over y times y becomes just 1. And now my last step to get my y isolated on my left side, I end up with 1 over x. Now, don't you notice that this is actually the same result as the original function? Okay, this is actually the same rational. So we can replace y with f inverse notation because the inverse of the rational is just itself, actually. Okay? And you can see this as evident when you think about what the graph of the rational looks like. It has the two arms like so. And then when we think about what inverse means that we are reflecting on the line y equals x. But if you notice, these points will just reflect here, and then these points will just reflect here. But then the actual overall graph will look the same. That's why the inverse of the rational is itself. Very interesting end result here. For this next example, we have another quadratic, but this time, unlike on the previous page, we have the quadratic in standard form with more than one x term, okay, because it's in the form ax squared plus bx plus c. Right? That makes it very difficult for us to isolate for a single y, because right now if we switch x and y, we're going to end up with y squared here and also a y here. And how are we supposed to isolate for that? So instead, before we start trying to find the inverse, we're going to do something else first. So what we're going to do is we're going to write this out as y equals 2x squared minus 4x plus 2 squared minus 2 squared plus 3. So I hope that you've realized by now that I am trying to rewrite this function. Instead of in standard form, I'm trying to rewrite it in vertex form with a single x term. Okay, so I'm trying to complete the square here. So I factored out a 2 from the first two terms here. That's how I got this 2. So I got x squared minus 4x. And then I got this 2 by taking that 4, dividing it by 2, and then I squared it. And because I added that term, I also had to subtract. Okay, just a quick review of completing the square. So let's finish off. We have 2x minus 2 squared plus 2 times negative 4 plus 3. We're going to finish off. We have 2x minus 2 squared, negative 8 plus 3 minus 5, and that is our quadratic function in vertex form. So now we can go through the steps of finding the inverse. So we're going to switch x and y. And now we're going to add 5 on both sides. So that gets rid of the minus 5 on the right side, moves it to the left. And now we're going to divide both sides by 2. That gets rid of the 2 from the left side. And then we are going to have, so I'm just going to rewrite this in this format instead, half x plus 5 equaling y minus 2 squared. But instead of the squared here, what I'm going to do is I am going to simply take the plus minus square root on the other side, like so. And that will get me my y minus 2 without the square. So then my final step will be to add the 2 to both sides. So I'll get root plus minus root half x plus 5, and then on the outside plus 2, and that will equal y. And because this is just a relation, not a function, because of the plus minus here in front, I'm just going to leave this as equals y rather than equaling f inverse, for example. And that's my final answer. Okay. And the last example here, we have x is equal to 3 over y minus 4 minus 2. So in order to get this y minus 4 isolated, which is our ultimate goal here, the first thing we're going to do is move that minus 2 to the other side by addition. So we have x plus 2 equals 3 over y minus 4. And then in order to get this y minus 4 out from the denominator of this rational, we are actually going to take both sides and multiply by the entire denominator, y minus 4. Okay, so what that will do is, on the left side, we're going to end up with y minus 4 x plus 2, and on the right side we will have just a 3, because this y minus 4 in the denominator and this y minus 4 that we multiply by in the numerator will simply cancel each other out. So on the right side you'll just be left with this 3. Okay, and the reason why we want to do this is because now, in order to get y minus 4 by itself on the left side, you can simply divide both sides by the entire binomial x plus 2. And that will then give us, on the left side, y minus 4 equals 3 over x plus 2. And then our final answer is going to be to move the 4 over to the other side. That'll give us 3 over x plus 2 plus 4 equaling y. And now if you notice, the original function was a rational because we had x minus 4 in the denominator. And this inverse is actually also a rational because we have x plus 2 in the denominator. So instead of writing y, I'm actually going to write down f inverse, because I know that this is a rational function. Okay, so that'll be my final answer. In the next section of the notes, we're going to learn how to test for inverse relations or functions. So in order to do that, we're going to look at the previous page's example, f of x equals 4x minus 8. And then we're going to take the inverse of that. We're going to call it g of x for the purpose of the notes here. So we're going to say this is g of x. The inverse is x plus 8 over 4. If you prefer to use the slope y-intercept form, you can write this as 1/4 x plus 2. Doesn't matter. So now what we're going to do is we're going to simplify f of g of x. So what this means is I'm going to replace the g of x with x plus 8 over 4, because that is what g of x represents. Okay, so in the place of g of x, I plugged in x plus 8 plus 4 over 4 rather, sorry. So now what this notation means is, if you take a look at this original function up here, wherever you see x and x, they match up. Okay, so now if you see x plus 8 over 4 in the spot of this x, then that means you also need to replace this x with x plus 8 over 4. So let's write that down. So we have, we're going to rewrite this as 4 times x plus 8 over 4 minus 8. Okay, so all we've done is we've replaced these x's here with g of x through substitution. Okay, and now that we've done that, we can now simplify. 4 over 4 will just cancel out to give you 1. So then we're going to be left with x plus 8 minus minus 8, which will give you simply x. Okay, now let's do that the other way around and see if it gets us the same result. Okay, so this time I want g of f of x, which is f of x is 4x minus 8. So that is this f of x here. Okay, so I'm replacing f of x with 4x minus 8. So that means I need you to now take this x and replace them with 4x minus 8. So that means we're going to have 4x minus 8 and then plus 8 all over 4. Okay, and then we're going to end up getting in the numerator 4x minus 8 plus 8, well, the 8 and minus 8 and 8 will get 0. We'll get 4x over 4, which will give us x. Okay, so what we should notice about the result is that both f of g of x and g of f of x will give us the result of x. And this is because the inverse means to do the opposite operations in backwards order. So the operations of g of x will cancel out the operations of f of x and vice versa. So our key idea summary here, when g of x is the inverse relation of f of x, and vice versa, that f of x is the inverse of g of x, we can conclude that when you substitute one function into the other, either f of g of x or g of f of x, they will both give you the result of x, specifically when f of x and g of x are the inverses. Okay? So let's go over this example. We're going to apply the inverse test to determine whether or not f of x and g of x are inverses of each other. So I am going to take f of x and I'm going to substitute in g of x. So I'm going to substitute in 1 over 2x minus 2 into my f of x function. So over here, this is my g of x function, which I am going to substitute in for this x right there. So I get 2 over 1 over 2x minus 2, and then I'm going to add 1. Okay. When I do 2 divided by anything, that means that instead of dividing, I can multiply by the reciprocal. So this is going to end up giving me 2 times 2x minus 2 over 1 plus 1, which when I expand and simplify, I'm going to end up getting 4x minus 4 plus 1, which gives me 4x minus 3. Okay. Automatically, I can see that this is not going to equal x. So this test will be enough to disprove that f of x and g of x are inverses of each other. Okay. I will show you g of f of x as well, just in case you wanted to try it the other way around. So if you wanted to try g of f of x, then that means this time you're going to sub in 2 over x plus 1 here in the place of the x in g of x. So that means this is going to give us 1 over 2 times 2 over x plus 1 minus 2. Okay, so that f of x, which is 2 over x plus 1, we substituted into the place of the x in g of x. So again, when you simplify this, you will end up with 1 over, this is going to be 4 over x plus 2 minus 2, which is going to give you 1 over 4 over x, which is x over 4. And obviously, this also does not equal x. So we can conclude that, therefore, they are not inverses of each other. But when it comes to word problems, we're going to have to do things a little bit differently when dealing with inverses. So this is an example from the textbook. The relationship between the speed of a car and its stopping distance can be modeled by this quadratic function, d equals 0.006v squared. So that is essentially quadratic function vertically compressed by a factor of 0.006. So this is not going to be an accurate sketch. It's just going to be a very, very, very rough sketch right there, okay? So, and it's just the half of the parabola, because if v represents speed, speed can't be negative, okay? So we're going to use that for our domain. So domain, usually for a parabola, would be any real number such that there would be no restrictions. But in this case, we're talking about speed. Speed can't be negative, so we're going to say that v has to be greater than or equal to 0. And then for the range, okay, this is a parabola. Again, if your speed is 0, then your stopping distance is also going to be 0. So that means that we're going to write d is any real number such that it is greater than or equal to 0 for the range. Okay. Now we're going to sketch the graph of the inverse. We're going to determine the algebraic model for the inverse. And then we're going to state the domain and range of the inverse. So on your x and y axes, what I need you to do is write down on the x-axis, it's now stopping distance d. And on the y-axis is now your speed v. Okay, so that means that when your stopping distance is 0.006, then your speed was 1 kilometers per hour right here. Okay. So because we switched the position of d and v, we are not going to switch the variables in the algebraic model. So I want you to keep the original algebraic model as is, and we're not going to do the whole switching of the dependent and independent variables. We don't need to do that because we already switched them here on the x and y axis. So instead, what we're going to do is we're just going to work on isolating our v now. So we're going to divide both sides by 0.006 first, and then we're going to take the square root. Okay, but because this is a real life situation, we're not going to have a negative square root. Okay, so we're going to disregard that negative, and instead we're just going to keep v as positive square root stopping distance divided by 0.006. Okay, so that means that our domain and range is now going to be switched from the original domain and range. Okay, so domain is now talking about the possible values of d, stopping distance. So d is any real number such that it is greater than or equal to 0. And for the range, v is any real number such that stopping speed is greater than or equal to 0. So you can see that when it comes to word problems, don't switch the variables, okay? Just isolate for what used to be the independent variable, because now the independent and dependent variables, they switch, okay? So that's the first part of our lesson on inverses. For tomorrow's lesson, we're going to talk about what specifically we need to do in order to ensure that the inverse actually is a function itself.